Hi guys, we're going to be talking about dual selection. So a dual selection is a great way of engineering basic biological activity. This is going to be more of a Cliff Notes version of it. So we're going to start off with a library. And let's, for argument's sake, say that it is a promoter library. So we have promoter library. And we want to find a promoter that is going to give us a specific biological response to some sort of molecule. Let's say we'll call molecule M, which is some sort of metabolite maybe. So when we think about our library is going to be composed of three basic groups. If we make a pie chart, we're going to have the majority, which is going to be here, is going to be constitutive off. Dead, don't do a darn thing. And then the second largest population will be constitutive on. That means they're just stuck on all the time. Kind of the mirror opposite of the constitutive off. And then a very, very tiny segment, which is so small you probably wouldn't even be able to see it here, is going to be the inducible. And we want to get that inducible. So in order to find the inducible clones from the library, we can use that dual selection. So the dual selection is actually not one selection, but it's two selections. It's a negative selection and a positive selection. So a negative selection, also known as a counter selection, will remove anything that is constitutively on, and a positive selection will remove anything that is constitutively off. So what the dual selection does is it uses these two types of selections in order to get rid of the constitutive phenotypes and hopefully leave you with the inducible phenotype. So let's just kind of go through what's going on here. So we have our library. And again, it's all these different promoters that look different. We transform our library into our cells that we're going to do our selection in. And at this point, we can think of our cells, or rather our library members, as constitutive off, constitutive on, inducible, and we're going to do the negative selection. So in order to do the negative selection, we want to get rid of anything that is constitutively on. So we're doing a selection for negative activity, a counter selection. We're selecting against activity. So in order to do that, what we're going to do is we're going to attach the transcriptional output of our library to some sort of counter-selectable marker, some sort of poison. So an example might be CCDB, which will kill the cell if it gets expressed. So if this promoter is active, this gets transcribed, your cell is done for. So that when we perform our negative selection, all those constitutive on mutants that were driving CCDB, they died. They produced it, they were constitutive mutants, and that's no good, so they're gone. And that's essentially the negative selection. Gets rid of those constitutive on mutants, and the output of that negative selection is only cells that are constitutively off or inducible. So one more time, just to kind of stress what went on, is we attached the output of our library member to a counter-selectable marker, so that the constitutive on produced that counter-selectable marker and killed themselves, leaving only the constitutive off and the inducible. So we're halfway through our dual selection. The next phase of it is the positive selection. So we've gotten rid of the constitutive on. Now we need to find something. We want to find our clone that is going to respond to our molecule M. So during that positive selection, what we're going to do is we're going to induce with M. So that means we're going to throw a little bit of M into our media or into our plates or whatever, however we're doing our induction. And then we're going to do that positive selection. And in order to do the positive selection, we're going to attach the output of our promoter. Instead of attaching it to a poison, we're going to attach it to like a positive selectable marker like ampicillin or chloramphenicol or whatever, your favorite antibiotic. And you're going to hopefully see a promoter that will respond to M and turn on. So once we plate our library that has undergone induction, it's being induced, and it's plated on this selective condition. So if this gray thing is our plate, we'll say it's an AMP plate. What's going to happen is that those constitutive off are not going to respond to M. They're not going to do, so if here's M, M doesn't do a damn thing to our promoter, AMP does not get produced, and they die. They're gone. They do not have the ability to produce M. They are not biologically active, whereas the inducible clones, they will respond to M, and they will produce that ampicillin, and they will survive, so that, you know, we get a plate with a few colonies on it, and those colonies that survive that positive selection, they also had to have survived that negative selection, which means that they remained off without induction in order to pass that negative selection, but specifically responded to M in order to produce antibiotic resistance in order to survive that positive selection and form colonies. And those colonies should harbor plasmids that, again, are the specific biological activity that you were doing the entire dual selection to begin with in order to find. So again, this is a great way of engineering high specificity biological activity, but like all indirect genetic selections, it has problems. They're kind of complicated. There's a lot of tuning steps. You got to figure out what the expression levels are going to be. There's contamination issues. There's a lot of steps to these, so they're hard to do. And also they're kind of low yield, and there's contamination issues. But if you have some time and you really want to engineer some specific biological activity, this is a great way to do it. And it is it's a very, you know, it's a great idea. So if there's any questions, let me know and I will try to answer them.